Hey everyone. So we did a couple of examples of graphing, well, we did one example of graphing rational functions today in class. I wanted you to have a couple more to help you with this, especially because I want you to get started on homework 10 over the weekend. I want you to have a couple of examples to help you through it. So in order to graph a rational function, the first thing that you're going to do is find the location of holes and vertical asymptotes. These guys come from the domain of your rational function. And again, domain of a rational function, those are the places where your denominator equals 0, essentially. We don't want to allow our denominator to go to 0. And the places where our denominator is equal to 0 create holes and vertical asymptotes, because those two things say, hey, I can't have an x value here, because if I try to plug x in, my denominator is 0 and no y value comes out. That's kind of what these guys mean. So to find the location of any holes, these come from factors that cancel. To kind of refresh your memory on that. And vertical asymptotes come from any factors on the bottom that don't cancel. So everything, once you factor the top and the bottom, anything that cancels creates a hole, and everything left on the bottom that doesn't cancel creates a vertical asymptote. And you'll see exactly how we find those when we get to the example. The next thing that you're going to do is find your end behavior. Again, to do that, you're going to do your end behavior fraction, and you're going to do the leading term on top over the leading term on the bottom. This creates your end behavior fraction. You're going to simplify that, and whatever that thing goes to as x goes to infinity creates your horizontal asymptotes. We did that in class as well. And finally, I want you to calculate your x-intercepts. To find your x-intercepts, you're going to set the numerator equal to 0. So any factors in the numerator that don't cancel will create x-intercepts. So to kind of match the way that I did this up here, your x-intercepts come from factors on the top that don't cancel. Those guys create x-intercepts. And then once you have all of this, you're going to plot your holes, your x-intercepts, and your asymptotes on your graph. And then you're going to make sure that you have 2 points on either side of every vertical asymptote. You'll need these for Alex. It's also going to help you fill in if you have to fill it in by hand. And again, to do that, you can just pick any x values that you like wherever you need them, plug those x values into your simplified function, and then get those ordered pairs and plot them. And then you're going to connect your dots and go to your asymptotes. That's how you're going to fill in your graph. So let's practice this. Again, I'm going to come back to number 1. That one's a little weird. So I'm going to come back to that one. Sorry, I'm doing these all out of order. But I want you to, before we get to that one, we'll just kind of work with more typical rational functions, because number 1 is kind of, it's more simple, I think, but something weird happens there. Okay, so we're going to start with number 2. In order to start this, we are going to find our holes and our vertical asymptotes first. So we're going to factor the numerator and factor the bottom. So factor top and bottom to do that. On top, I can take out a 2, and we'll get x plus 3 up here. And I need to factor the bottom. That factors into x plus 1 times x plus 3. All right, so now that we have it all factored, if anything cancels, if any factors cancel, which we have one here, that x plus 3 on the top and bottom that cancel is going to create a hole. So I have a hole at the x value that makes that factor equal to 0. So the x value that makes x plus 3 equals 0 is x equals -3. That's where my hole is. Once we identify that we have a hole, go ahead and cancel the things that can cancel. We don't want to get rid of those until we identify and take note of our holes. But now that we've done that, we can get rid of our holes and simplify this thing. So basically, what we have left is 2 divided by x plus 1. What that means is that this original rational function is going to look exactly like the graph of 2 over x plus 1, except that we have this hole here. Because this x plus 3 cancels, it doesn't actually change the shape of our graph at all, which is why the shape is going to match what's left. But x can't be -3 because I have this x plus 3 on the bottom. So that's why a hole is what it is. So now we simplify and cancel, and we can use the simplified version for the rest of our stuff. And a hole is technically an ordered pair. So to get your y value, you're going to take this x equals -3 and plug it into this simplified version here. And so the y value at x equals -3 is going to be 2 divided by -3 plus 1. That's going to be 2 divided by -2, which gives us -1. That means overall, our hole is going to be at the ordered pair -3, -1. So I'm going to have an open circle, a hole at that ordered pair. Okay, so the next thing is our vertical asymptotes. Vertical asymptotes come from any factors on the bottom that don't cancel. We have this x plus 1 left on the bottom. So wherever x plus 1 equals 0, that's where my vertical asymptote is going to be. So my vertical asymptote is going to be at x equals -1. So I have a vertical asymptote there. And so that's our first part. We've done our holes and our vertical asymptotes. Those come from the domain where our denominator is equal to 0. And now I want to find my horizontal asymptotes. Those come from end behavior. So I'm first going to find my end behavior fraction here. End behavior fraction is leading term on the top. The leading term on the top of this fraction is 2x. Over the leading term on the bottom is x squared. So leading term on the top divided by leading term on the bottom, if I simplify that, I get 2 over x. So that's my end behavior fraction. To find my horizontal asymptote, I need to figure out what happens to 2 over x as x goes to infinity. So as x goes to infinity, 2 over x, this actually goes to 0. We talked about this in class, but just to help you with that in case it didn't make sense, we're going to think about what happens to 2 over x as our x values get bigger. So we'll start at 1. And if x equals 1, then 2 over 1 is 2. Let's make x a little bit bigger because we want x to get really big eventually, but we'll work our way there. So if x is 10, then 2 over x is 2 over 10, which is 1/5 or 0.2. If x gets even bigger to 100, then 2 over x is 2 over 100, which is 1/50th or 0.02. If x goes to 1,000, then 2 divided by 1,000 is 1 over 500 or 0.002. We can keep doing this. We can go all the way to 100,000. Let's see what happens as we go all the way up here. This is going to be 0.1 1, 2, 3, 4 zeros, and then a 2. And this is going to keep going. The bigger this thing gets, the smaller this gets. So we're actually going to have 8 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 2. So basically what happens is the bigger x gets, the further out that 2 gets. We get more and more and more zeros here. This number is getting closer and closer and closer to 0. So as x goes to infinity, this 2 over x is going to go to 0. Now, what that means for us practically here is that because 2 over x goes to 0, and that's our end behavior, our whole function is going to do the same thing. That means our function, our y values are also going to go to 0, which means we have a horizontal asymptote at y equals 0 at the ends of our graph. And again, this is as x goes to infinity. This is end behavior, and horizontal asymptotes are really just asymptotes at the ends. All right, so we have our vertical asymptote, and our horizontal asymptote. Last thing I want to find is our x-intercepts. The x-intercepts come from any factors on the top that don't cancel. So here we have a 2 left on top. So what you would do is take your numerator, set it equal to 0, and solve for x, and that would tell you where your x-intercepts are. If I set my simplified numerator here, what's left up there, 2 equal to 0, I don't have an x to solve for. 2 is not 0. It doesn't matter what x is, 2 is never going to be 0. What that means is that this thing actually doesn't have any x-intercepts at all. So this thing doesn't cross the x-axis anywhere. Okay, so now let's graph this thing. So I'm going to erase all this so I have room to graph. And let's graph this here. So just going to make my axes here. Okay, so I have a hole at -3, -1. So x is -3, y is -1 is down here. There's my hole. It's just going to be an open circle. I have a vertical asymptote at x equals -1. So here's my vertical asymptote at x equals -1. And I have a horizontal asymptote at y equals 0. So here's my horizontal asymptote at y equals 0. Now, I don't have any x-intercepts to plot, so this is all the points that I have. Now, Alex is going to want you to have 2 points on either side of your vertical asymptotes. So our hole here counts as a point because our graph is going to have to go through that hole. And we need another point over here. So we're going to pick an x value to the left of our vertical asymptote. You can pick any x value you like. I'm going to pick this one, which is -2. So for my extra points, I'm just going to say x equals -2, and I'm going to plug it into the simplified version. You can plug it into your original as well if you like, but I'd rather plug it into my simplified version because my simplified is less scary. So I'm just going to take the path of least resistance here. So if x is -2, y is going to be 2 divided by -2 plus 1. That's 2 divided by -1, which is -2. So I have an ordered pair at -2, -2. So I've got one at -2, -2. Here's another point over here on the left. I also need 2 points on the right side of my vertical asymptote. I don't have any points there at all. So I can pick whatever I want over here. So I'm just going to pick, how about x equals 0? If x equals 0, then y is going to be 2 divided by 0 plus 1. 2 divided by 1 is 2, which means I have the ordered pair 0, 2 over here. And how about x equals 1? Just kind of keep going. Y equals 2 divided by 1 plus 1. That's 2 divided by 2, that's 1. I have the ordered pair 1, 1. So I'll plot 1, 1 right here, and I've got 2 points over there. Now on Alex, this is the point where you would hit a graph a function button, and Alex would just fill this in for you. If you were on a test or a quiz and you need to fill this in, I want you to connect your dots. So if I start at 1, 1 here and connect it to this 0, 2, I'm going to connect my dots and then head toward my asymptote. Your asymptote acts as guides, and so you're just going to go toward that asymptote and go right up next to it. And we'll also go the other way. So we'll start at 0, 2, head down to 1, 1, and then keep going down to your asymptote here as well at the ends. So in the middle, you're going to go up or down to your vertical asymptotes. And again, connecting these dots will help you figure out if you're going to go up or down. And your horizontal asymptote, you're also going to kind of hug that line and head toward your horizontal asymptote. So again, we'll do this over here. So I'll start at this -2, -2. I'm going to come back up to my hole here at -3, -1. And then I'm going to keep on going to my asymptote. So we look something like that up here. And then if I start at my hole and then go down to -2, -2, keep on going. And so we're going to go down to our vertical asymptote. If you start by connecting the dots that you have, that'll help you figure out if you're going up or down. So here's what this rational function looks like. Cool. All right, let's head back up to number 1. So I said this one's going to be a little bit different. And I wanted to do this one so that we could kind of see what a hole does. Again, this x plus 3 canceling, it doesn't change the shape of our graph. The rational function that we graphed down here is actually the graph of this guy. But the graph of this thing is actually exactly the same as the graph of 2 over x plus 1, except that the one that we graphed has this hole here at -3, -1. The graph of just 2 over x plus 1 would not have this hole here. But our function does because of this extra x plus 3 factor. So the holes don't actually change the shape of your graph. They just poke a hole at the x value here. So with that in mind, let's come back to number 1, and we'll kind of do this the way that we've done so far. So we're first going to find our holes in our vertical asymptotes. To do that, you're going to factor numerator and denominator. So our numerator here factors into x plus 6 times x minus 2. And again, to find that, we needed 2 numbers that multiplied to -12 and added to our b value of +4. So those 2 numbers were +6 and -2. Since our leading coefficient is 1 here, I could just pop those into parentheses with x's. So the top's factored, the bottom, there's really nothing to factor there. And so now I have a common factor on top and bottom. That means I'm going to have a hole. And I'm going to have a hole at the x value that makes that 0, which is x equals 2. So I'm going to have a hole at x equals 2. And so now that I've made a note of that, I'm going to cancel that common factor and simplify what I've got. Notice that x minus 2 is the only thing that I had on the bottom. All I have left is x plus 6. Now, what we've done so far, we know how to finish this whole. To get the y value, I'm going to plug x equals 2 into my simplified version. So y is just going to be 2 plus 6, which is 8. That means my whole, and I can't spell. Let's try that again. The whole for my function is at 2, 8. Okay. Now I don't have anything else left on the bottom. So basically I don't have anything down there to create any more vertical asymptotes. So this thing has no vertical asymptotes at all. And we could continue finding our horizontal asymptotes. Um, if you did that, you would find your end behavior fraction. Our end behavior fraction would be leading term on the top divided by leading term on the bottom. When you simplify that, you get x. So that means that this function acts like the function y equals x at the ends, which means this does not have any horizontal asymptotes. This acts like a polynomial at the end. You could do your regular end behavior from before. If you do that, you'll find that your end behavior looks like this. And I know I'm speeding through this, but I kind of want to point something out. And then to find your x-intercepts, you would take your numerator, what's left, which is x plus 6, set that equal to 0 and solve for x. So that's negative 6. That means you have an x-intercept at negative 6, 0. Now, what a hole does is it doesn't change the shape of your graph, it just pokes a hole. Because our x minus 2's canceled and we had a line left, y equals x minus 6, the graph of what we started with is going to look exactly like the graph of y equals x plus 6, which is a line, but with a hole. That's why I don't have any vertical asymptotes or horizontal asymptotes, because this is actually going to look just like the line y equals x plus 6, but with a hole at 2, 8. So I'm going to go ahead and put my hole at 2, 1, 2, 3, 4, 5, 6, 7, 8. My hole is at 2, 8. I have an x-intercept at negative 6, 0. 1, 2, 3, 4, 5, 6. And notice I have polynomial end behavior like this. I'm actually going to do one of these, because this is the line y equals x plus 6, except with a hole here at 2, 8, because of this extra x minus 2 factor on the top and the bottom. So that's basically what a hole does. It doesn't change the shape of your graph, it just pokes a hole. So the fact that when we simplify this and basically take our hole out, we get a linear function. So this is just a line with a hole in it. It's kind of a weird one. All of our rules for vertical asymptotes and horizontal asymptotes and x-intercepts still apply. I just feel like this one is kind of a weird one, and I didn't want to start with it because it's such a special case. But I think this one is really nice because it really shows you what a hole does. Doesn't affect the shape, it just pokes a little hole. All right, so that is a couple of extra examples for graphing rational functions. I hope you have a chance to do this over the weekend, and I'll see you next week.